Hello everyone, good afternoon, and welcome to the OneClass channel. My name is Fejiro, and I'm an Honors Bachelor of Science graduate. I'm sure you've seen my face a couple times now. Right now I'm currently working towards medical school, but for today actually we'll be going over some commonly asked chemistry questions at both the high school and college levels. If you need some extra help, whether it's with your homework or just some tutoring, please feel free to check out the links in the description below. And so with that, we're going to kick this right off with the first question of this session. It's going to be, let me just switch this over now. Hopefully you can see the screen. We have, what is the molar mass of H3PO4? Okay, so let's just write that down. Mass of H3PO4. So with this type of question, it's all about getting familiar with your constituents. As an extra bonus actually, I know that you guys can't actually hear me, but I want you to give me what you think this element is called. Okay, so remember, when you break it down to its constituents, we have H3 and we have PO4 3-. So what is that ion? So this, because we have a phosphorus, so we have FOSP, FHOSP, and then because we have that O, the oxygen, okay, we actually end with ATE. So this is a phosphate ion. And when you have a phosphate ion, you want to drop this part here and just make it into an acid. So, but phosphorus has a slightly different naming rules. Instead of just being phosphoric acid, it's going to be phosphoric acid. So you see how it's different there because you added the hydrogens to the phosphate ion. And just make sure that we actually have that name right. Phosphoric acid, H3PO4, should be a strong acid. Oh wow, who knew? It's actually not a strong acid. That is new. But yeah, phosphoric acid right there. Perfect. But now to actually answer the question, that's what it's asking for, the molar mass. We get a constituents. So we have 3 hydrogens. And then we have 1 phosphate. And we have 4 oxygens. Okay? So hydrogen, according to the periodic table, has 1.008. Yep. Phosphorus has 30.974. And oxygen has 15.999. And so we multiply everything together. So that's 3.024, 30.974. and 63.996. Okay, and don't worry, it's not that I just know how to do math real fast. I've just seen 4 oxygens multiply so many times. So now we just add them together. See, I need a calculator for this part. 0.974 plus 63.996 plus 3.024. So we get 97.994 grams per mole for the molar mass of phosphoric acid, aka H3PO4. Okay, did I do something wrong? Phosphorus, right? Let me see. Yeah, 30.974, and they have, oh, they missed a 0. Okay, and you know what? These type of questions as well, it's always good to really just, because it is quite a common molecule, so you can always check on the internet. Yes, so I just want to make sure I wasn't seeing that wrong. So where they did it wrong was they missed a 0 in phosphorus. It should be 30.97, not 39.7. So this is incorrect. AMU for phosphorus is 30.97, not 39.7. So yeah, small mistake there, but that's why it's very important to always check your numbers, which is why I was taken aback a bit when I saw something different. But yeah, so that is a breakdown of the molar mass of phosphorus. Phosphoric acid. Mainly this part here. You don't have to really worry about the naming, but if you were trying to familiarize yourself with the names, that's there as well, just as a breakdown of how we got phosphoric acid, okay? So with that, we're good to move on. Let's see what question 2 has for us today. Depict the electron configuration for magnesium using an orbital box diagram and noble gas notation. Give a complete set of 4 quantum numbers for each of the electrons beyond those of the preceding noble gas. Wow. That's definitely a lot. So the first thing, just so that we don't forget, we want to make sure that we remember our, the quantum numbers. So we have, I believe it would be N, then L, then I believe it's M, or is it minus L and then M? No, let's see. It's N, okay. It's M and then the M in between. The ML and then the MS. That part, these two are always the hardest ones for me to remember. And so just as a trick for you to remember is that once we actually do the question, you'll see that the ML is constituted of whole numbers typically, and MS is the in-between, so the halves. Okay? But before we delve into that, the question first is asking for the electron configuration of magnesium. So with that being said, let's look at magnesium. It is on the 3rd row, 2nd column. So they said using the noble gas, right? Meaning that you want to start on the most recent noble gas before you get to magnesium. So like it wouldn't be helium, it wouldn't be argon, it'd be neon right here, because this is the noble gas preceding magnesium, since the periodic table goes like from left to right as you read it. So as you keep going from left to right, you'll see that the noble gas before magnesium was neon. So that's what we do here. And then to be able to get the electrons, what they're referring to, it's gonna be in the s orbital, because we're dealing with the first 2 columns. The p orbitals delve into from column 13 to column 18, excluding helium. And then the d orbitals are from column 3 to column 12. And then the f orbital is the lanthanum and actinium series. So we're in the s orbital, so it's 3 s, that's the 3rd row as I mentioned. S is where we are, and then magnesium is the 2nd element, so that means it has 2, so 3s2. Okay, so now this is what we have here for magnesium. Okay, now the N is referring to its orbital shell, like what orbit is it on. As we mentioned, it's on this 3rd orbital, so N is equal to 3. Okay, and before we even go any further, actually, remember how I mentioned there's 2 electrons there? If you wrote this in orbital notation, neon would look like that's what I forgot to do. It looks so blank. We need some context here. So we need to actually write down what the question is. So the question is asking to depict electron configuration of magnesium. You just say magnesium, so that's Mg, using orbital notation, which we've done right there, with noble gas. Okay, and give quantum numbers for electrons. Numbers for valence electrons. Now, actually, you know what? I'm going to just say for electrons, I'm going to say what they said, because there's some times where there are electrons beyond the noble gas, but it's not a valence electron. A good example is when you get into the D and the F orbitals, those shells, those ones technically are still in the prior orbitals, so they're not in the valence electron just yet, if that makes sense. Because D, it would actually, let's say we went all the way down to, as an example, copper. Okay, it wouldn't be 4D here from all these, it would actually be 3D. So it would actually be from the third orbital. So it doesn't count as a valence electron. So, but still, you would still indicate that in your electron configuration, even with the element there. So like if I was to quickly do copper, it would be argon, okay, and then 4S2 because that one's filled over there, and then 3D9. You see how that, even though this technically this is incorrect, but this is an example. 4S2 3D9, you rearrange it, the argon, the noble gas is still there, and because it's one of the ones you have to memorize, that's just how it will turn out, because it wants to fill its D orbital first, considering it's the lower orbital. It usually likes to fill it if it has the energy required to do so, and if it's more convenient for it. But point being is that typically for copper, right here, it usually has one valence electron, or at least one electron wants to give away, in most cases. Now, with that being said though, this is just a side example, so we can just ignore that. Back to the question at hand. Numbers for electrons beyond noble gas. Okay, so we've done that. Now, as we said, we have 2 electrons, okay? Because it's 3s2. Not the shell indicates, but the actual number, that small one up there, indicates how many you have. The orbital configuration, okay, same thing, but you just have a box instead, and it's only going to be the 3s, and you have in there 2 electrons, just like that. And they're asking for the numbers for those 2 electrons, okay? So electron 1, okay, would be n equals 3, L is equal to, now, this is what you have to memorize. When it comes to S, P, D, and F again, the S subshell has an L value of 0, okay? Just 0. The P subshell has a value of 1. The D has a value of 2. And the F has a value of 3, okay? And now, that's what we actually put there, 0, okay? So, the ML, the way to calculate that, funny enough, is to give every possible value that it can be. But since it's just 0, like every positive negative value, the ML would just be actually 0 as well. Now the MS, that's the part that gets a little bit trickier, okay? I'm actually going to look into what they did here, because I had a feeling exactly. The MS indicates what type of spin it has. So, oops, sorry, I definitely did that one wrong then. No, that's correct. Okay, now it's starting to make more sense. So, the spin is pretty much, how do I put this? It's like, the direction is going, hence we have the up and down arrows. So the up is positive, right? But it's not a whole number. As I mentioned, it kind of works in halves. It's like the in-between step. It would be 1/2 only for the first electron, okay? Now, electron 2, okay, once again, N is equal to 3, L is equal to 0, because we're still on the s orbital subshell. The ml, because it's every possible combination, like positive and negative value of 0, it's going to be 0 as well. But now it has the negative spin, as in the opposite spin as the first one, as in the 1/2. So with that being said, that ms for the second one is going to be minus 1/2. Okay, and you'll notice that I guess to really delve into it, that these two should technically always, the two MS's, if the shell is full, should equal 0. Like it should match the ML, hopefully. But yeah, that would be the way to depict the electron configuration. Okay, we've done that here. And I also wanted to show this picture because this also explains how we have 2 electrons as well. And these are all the quantum numbers for them. So as a quick review, it's on the 3rd shell, okay? The S subshell, which makes L equals 0. Every positive and negative value of that number, which is still 0. So say we were at the P shell instead. What would actually happen is that ML, well, L would equal 1, and ML would equal -1, 0, and 1. Those are the 3 possible things it can be. And for the last one, MS tells you like what spin it has, hence how we have this. So these are all the numbers. Let's see how we did officially. So exactly, electron configuration, 3s, up and down. Perfect. Okay. And let's see here. What else we have? For n equals 3, possible values of L are 0 to 2. But since we're in the s orbital, L is equal to 0, exactly. As I mentioned, the way it works is that we have 3, 0 in a sense, because that's an S. 3 right here, because that's a P. Okay. And then 3, D is this one here. And technically we don't really have a 3F. The first F starts at 4, because it's like 6 minus 2. F is 2 minus. Okay, so that's what it did. Since we're in the s orbital, L equals 0, that means ML for L is just 0 as well. And then there's an upspin plus 1/2, and the downspin is minus 1/2. So I guess the way the spins work is that you kind of add a half for the spins. So exactly, if your ML value was 1, you would have an electron spinning at 1.5, and the other electron spinning at -1.5. I believe that's how it works, but we'd have to delve more into it just so that way we have the actual values for it, because I do know that it's usually the in-between values between 0 and 1. So with that being said, let's see what we have here. These are both correct. Yep, the biggest difference is the plus 1/2 and the minus 1/2. So this is correct. Okay. Electron configuration, that's always a tricky subject, especially when you start dealing with the actual quantum numbers, because things can start looking very familiar. And the question they typically ask you is something like, is this a viable quantum number for an electron in this shell? So you kind of have to make sure you cross out everything it can't be. So with that being said, question number 3 is how to calculate pH of acetic acid. Okay, so with that being said, there's actually a lot of steps we need to take to calculate the pH of acetic acid. First step, honestly, I think is the most important, is to verify / find Ka of acetic acid. Okay, and you're probably asking why? Because we want to know if it's a strong or a weak acid. If strong or weak acid. Why do we need to know that? Because based on knowing whether it's a strong or weak acid could save you a lot of work. Strong acids and weak acids dissociate differently. The key separator is that if K is greater than 1, strong acid. If K is less than 1, oh, I have my signs wrong. Almost did it again. K is greater than 1, less than 1, weak acid. Okay? So, they don't say it, so this is more of a theoretical question, but that would be honestly the first step. So let's refer back to our acids and bases sheet. So, we have for acetic acid, where is it here? I think I passed it already. There we go, acetic acid. Okay? It has a value of 1.76 times 10 to the negative 5. So acetic acid is a weak acid. Now that we know that, we need to now use the corresponding equation then for the dissociation constant. So we have Ka is equal to the products, okay, which is going to be for acetic acid is conjugate base and H3O plus over its reactants, which is just going to be the conjugate acid. Okay, so to put actual values to it, if we have acetic acid, the formula is CH3COOH plus H2O. It doesn't count as a product because it is just part of the solution. It's an aqueous solution. It's in water, and it forms CH3COO minus. That's the conjugate base. Okay, plus H3O plus. Okay, so typically, actually, what you would see is that instead of CB and CA here, you would actually see A minus, because what's happened is that it just lost a hydrogen and HA there. So this is your HA and this is your A minus. So this right here is the formula for Ka. So if we're to bring it down to now for this specific acetic acid, it would be CH3COO minus H3O plus over CH3COOH. That right there would be your Ka. Now, with that being said though, okay, our work is definitely not done. The goal we're trying to do here is find specifically this, because this tells us, because remember that formula to find acids, the formula to find the acids, right? I mean, to find pH is just pH is equal to negative log H3O concentration of hydronium plus. That's really it. But the issue, the reason why is because it's a weak acid, we kind of have to go through a process to even get to this equation, okay? So with that being said though, we kind of have the equation set up and we want to solve for the H3O plus. But I wouldn't go and try to isolate it from this equation here. I would actually use what we call an ICE table, okay? Which stands for initial change and equilibrium. Okay, the reason why we do this is because whenever they're asking you to find the pH of, I guess, weak acids in general, they usually give you or any acid really, they kind of have to give you the concentration of the acid. Like if I want to find the acidity of hydrochloric acid, I need to know the molarity of it, the concentration, moles per liter. So that's the initial amount we start with of the acid. So here's CH3COOH. And then we also need to list down the products. And H3O. Okay, so now, as I said, we're given the initial concentration of CH3COOH. So let's just make it a value. Let's say it's let's use X, like big X. I guess that's the easiest way to put it. Okay, and these are gonna start at 0, because usually when you solve these questions, they just said like that's the concentration of the acid and there's nothing else added to it. You have yet to form any of the products yet. Okay, that's why we start at 0 for these ones. And then we are now to factor the change. If we're going based on this equation here, we're going to have one of these. It's a 1-to-1 ratio. For every CH3COOH lost, which is the only way to go because you need to form your products, for every CH3COOH lost, an amount of CH3COO and H3O of that same proportion are made. So it's like this: plus X minus little x. So that's why they want to use X. I'm going to use Z. That's something that I don't think I'm going to use in this one. Or quantity. That's a better one. Q. Initial amount. Yes. So our total equation now for this ice table is Q minus X, X, and X. And we're in a sense trying to solve for X, which is why I did want to rearrange this equation here, because it honestly just makes things harder for you. You want to solve for X because you know that whatever value you have of CH3COO minus is the same as that H3O plus, as long as you didn't start with any of those products in the beginning before you even did your work. Sometimes they may say like, oh, a weak acid was added into the into a solution that already contained a strong acid, so there's complete dissociation. So you'd actually already start with a certain amount of H3O already, and that would definitely affect your change in pH. But before we even get over there, point being is this is how you set up this equation. Now, this is the part we have to stress because there's a breakdown in terms of two methods to solve this, okay? And the methods depend solely on this right here, the Q minus X, okay? It will change this part. That's what I meant. If your concentration, okay, is 1,000 times greater, so it's still bigger than 1,000 times the Ka value, then effectively, so this is if this, then Q minus X can be rounded to just Q. If not, you have to keep Q minus X is equal to Q minus X. You're probably wondering, how does that play into this? When you're actually filling your values for the Ka, you actually see, so we're using acetic acid, right? We have 1.76, right, times 10 to the negative 5, yep, is equal to, okay, because we have two x's now, CH3COO minus and H3O, so that's x squared over either Q minus X or just Q. So let's say, exactly, we had a concentration of, let's see, 1.76 times 1,000. So if we had a concentration of 0.01 of the acid we're starting with, we have to use this one here, okay? And this actually simplifies into a quadratic formula. So you'd have to use a quadratic formula here when you actually reorganize everything. If it was greater than 0.01, so let's say we had like 0.02, like I would say minimum, that's a pretty good amount. You can kind of just round it off, okay, where you just have x squared over Q, which means all you'd have to do there is multiply the concentration times the K value, the Ka, and then just do the square root of it. So that's why there's two ways to do it. Okay, let me actually switch sides because That way it's a little bit more coherent. Okay. So, oops. So overall, the point being is that, let's see, where am I? This is the one I want. Okay. So let me just not mess that up again. So we have this. Alright, so one requires quadratic and one requires that. The quadratic equation, okay, would kind of end up looking like this. So you multiply both q 1.76 times to the 5 minus x of that amount. So it would be x squared plus 1.76 times 10 to the negative 5x minus q times 1.76 times 10 to the negative 5, okay? So, equals 0. So exactly, this right here is the b value you'd use in your quadratic equation. This 1 is your a value, and this right here is your c value. So you would have exactly the minus b plus or minus the square root of b squared minus 4ac and over 2a. That's what you use to solve this. You'll get two values, one of them being negative. That negative value you can just ignore because you cannot produce a negative amount of a product, okay? So exactly, that, all that work, whether you use this way or the quadratic equation, will give you an x value. That x value you get, okay, is going to be your concentration of H3O plus and also the concentration of your conjugate base, as long as both of them started at 0 initially. But you really just want the H3O plus. And now that we've gone the concentration of H3O plus, we can finally go all the way back and plug it into here to find out the pH of acetic acid. So, as a quick summary, if it's a weak acid, you have to go through these steps because that's what they said, acetic acid. The good news is that every weak acid follows this kind of breakdown where you need the Ka value and everything else. And exactly, you end up finding the concentration of hydronium, which you then finally plug in to find the pH. So, with that being said, fun fact, if it was a strong acid, it simply dissociates completely. So however much the concentration of the original acid, you'll have a proportional equal to that. So let's say you start with HCl, because there's only one hydrogen there when it dissociates. In fact, actually, because most acids actually just dissociate one by one, it would just be that it's a 1-to-1 ratio the hydrochloric acids put in. So then, with that being said, it's going to be whatever moles you have of HCl, moles per liter, the molarity, will be the same amount of hydronium. Hence why it's a 1-to-1 ratio there. Okay, so with that being said, we have, yep, pH equals negative log H. It's also H3O, that one works too. And then CH3COOH. I like to always include the water part because this is actually what's happening in the reaction. It's not really dissociating per se. It's more so that this water takes away the hydrogen from CH3COOH. Okay, so that's why we have the hydronium. And then we have the Ka value. Yep, 1.8 times 10 to the negative 5. Yes, that is actually what we have here. Okay, and then x squared, which is a CH3COO minus plus H, times H plus, over the Q minus X. Okay, oh, they use Z instead. Oh, close to using that, but exactly, see the Z minus X, and then you solve for X. And then the value of X substitution into equation 1, which is the negative log H, and then you got the pH. So exactly, depending on the concentration, is like you can either save yourself some work in just using that or the quadratic equation. If you're not sure, okay, which one you should use, default to the quadratic equation because that will always give you the most accurate answer. This equation here it's kind of just a rounding system you can use to save yourself some time if the concentration is so big compared to the Ka. So let's go on to question 4. Why is isotopic notation important? Okay, so this question is fairly loaded, because to understand why isotopic notation is important, you have to understand what isotopes are. Okay, so you notice how when you look at the periodic table, right, you have very specific numbers when it comes to like the atomic mass units. There's a reason for that, actually. It's a combination of the percentages of their isotopes. So isotopes typically are, you know, found, like, they're more like whole numbers when it comes to atomic mass units, because that's how they actually wanted to base the weight of them. So like a proton is typically around 1 atomic mass unit, or, you know, 1 gram, technically speaking. But going, like, delving into that, we can actually take an example of carbon. Okay, so carbon, okay, is going to be 12.011. What you'd actually see in nature, right, it's not a carbon that weighs this arbitrary number, but you'd actually have this type of carbon. This right here is an isotopic notation. What it's saying is that its total atomic mass units, okay, is 12, and it has 6 protons. Well, that's usually what it means in terms of that. Based on the elements itself, you already kind of gave yourself the first part of the isotopic notation. Like the bottom, the subscript to the subscript, so not the superscript, but the subscript to the left is usually going to match what the element is. Another example, let's say we had oxygen, right? It'd be, well, actually, before we even write that, we just want to focus on the actual element number. So exactly, a better name would be the element number, okay? And as we remember, element numbers indicate how many protons they have. So now you're probably wondering what the above number is, the superscript, okay? That one is a total amount of protons and neutrons in that isotope. So, with that being said, if I said this oxygen has 8 neutrons, okay, then that would mean that the total here would be 16. Now, that's just an example of isotopes. What makes this important is, as you notice, you see here, right, it's 12.011. Not every carbon, okay, comes in like that. Okay, there are some carbons that are actually like this. Okay, carbon 13 is what they call it. So this one will be called carbon 12, and this is carbon 13. Okay, so interesting enough, right? Although they do bond fairly similar, their properties themselves are slightly different between carbon 13 and carbon 12. Carbon 13 has an extra neutron, which just changes a little bit of constituents and what it can do in nature. And it's also, I would say, more unstable than carbon 12, considering that there's a lot more carbon 12s in nature than carbon 13. So, in a sense, isotopic notation tells us what type of isotope we're dealing with, because when you think about it, right, these, I guess, molecules and stuff that are formed, they're not just formed from like these elements, like of these arbitrary numbers, although that's how we get molar mass. It's kind of like the average, in a sense, of all the different types of carbons, because they still form the same bonds. They're still overall relatively the same thing, because they have the same amount of protons, same amount of electrons, but in terms of what they're actually made, like the neutrons part in the nucleus, it does make it react slightly different in terms of ways that even I'm not fully comprehensive in. But the point being is that that's when you start getting to things like whether it's purity and stuff like that, as in there are many things, whether it's the chirality in terms of like how it's structured, or even like what type of elements are bonded in it, that would affect molecules performance or how it functions. So in a sense, isotopic notation just helps us see what type of isotope we're dealing with. Okay, it gives us more information of how many neutrons there are. That's a key aspect. Okay, so for example, if we wanted to name this would just be oxygen 16, and I'm not sure what type of other oxygens there are, but so I don't want to list isotopes like that, but that in a sense is isotopic notation and why it's important. Okay, exactly. So let's see. Note that isotopes refer to all the variants of the same elements, while nuclide refers to an individual species with specific atom number and mass number. Okay. So let's see. Isotopic notation. Yep. A is equal to the amount of the element number plus the amount of neutrons it has. Okay. And they give you an example of lead. You see the difference between the amount of protons and the total amount. Sometimes there's exactly 125 neutrons. So that's pretty much what it's saying. How you break it down, you always want to subtract the subscript from the superscript to find out how many neutrons you have. Okay, exactly. And there's radioactivity, and elements that are more stable than others. For example, the reason why we have such a number close to 12 for carbon is because there's just more of these in nature, because they're just a little bit more stable than carbon 13. Okay, and you'll notice that as you get to bigger and bigger elements, that isotopes become quite crucial in explaining how you even get that atomic mass. Okay. So question 5. Let's see what we have here. What is the molar mass of H2SO4? Okay, so first question I'm going to ask, okay, this is going to go a little bit faster because we have solved a question very similar to this already. H2SO4. We did phosphoric acid, which was H3PO4. So I should kind of give you a hint at what this is called, because that's going to be the first thing I ask you. So remember, SO4, we have sulfate. I give it away. Whoops. We have sulf ion. Okay, but the O makes it have the ATE. So sulfate ion. Okay, and then you replace this part when you add the hydrogens in, so it becomes sulfuric acid. Okay, see, it dropped that and became sulfuric acid, not sulfic acid. You just have to make sure you balance it appropriate. So with that being said, same process: 2 hydrogen, 1 sulfur, and 4 oxygen. And as I said, when you've done it enough times, you get really used to the number 996. And sulfur, unfortunately, I don't have that one memorized. Not that good. Let's see here. 32.06. Okay. So 2 times that is 2.016. And 32.06. We add it all together. And 2.016 plus 32.06 plus 63.996. So really close, actually. 98.072. It's quite close to the other amount we had, which makes sense because sulfur is almost like makes up for that extra hydrogen, because it's just that much more heavier than phosphorus. It's about a hydrogen heavier. But yeah, so 98.072 grams per moles. So let's see what they did here. Yep, 2.016, 32.07, and exactly 98.086. Only reason why it's slightly different is because, let me see, just make sure I use the right ones. Yep, from their periodic table, exactly, that's what the numbers they were given. They were given 16 and 32.07 for sulfur. And that's actually why periodic tables can vary. It depends on how you round it, and also in terms of like the updated information, because in terms of like the isotopes and everything else like that, it's not really a constant number. These things do change as literally new discoveries are made in terms of which isotopes exist of that certain element. So that's why you can see the number change. It won't change drastically, but it can change slightly between table to table. Okay, so that's why, to play safe, I always say use a periodic table given to you by your instructor. Okay. And now, question 6. What is the molar mass of NaOH? So, we're going to approach this the same exact way. In terms of first, we'll just get the name of it. So, and then we'll just break it down to constituents. So NaOH, remember how we name certain things? We can tell from this is that when you separate it, we have sodium and we have hydroxide here. Kind of just have to memorize it. But the most important thing is that sodium is a metal, hydroxide is a non-metal. So together we have an ionic compound named sodium hydroxide. So with that being said, let's find the molar mass of this ionic compound. Just like that, 1, 1, 1. So multiply that, it'll be 22.99, 15.999, and 1.008. Okay, how do I know it's 22.99 for sodium? I've used sodium a lot. So 22.990, close. Same number, but you never want to forget any part of it, in case they're asking for things like, oh, what's the get it to the nearest significant digits. You can see that everything here except for hydrogen has 6 significant digits. It was 5, sorry, and hydrogen has 4. So we're going to write it based on the hydrogen significant digits, okay? Plus 1.008, because you always want to use your least sig digs, because that is where it's like, since you're kind of adjusting for accuracy, okay? So with that being said, we have 39.997, okay? Because we only need 4 significant digits, we round up, and actually we just get 40.00 grams per mole for sodium hydroxide. So exactly here, they had different values for it. If they were using oxygen, for example, as significant digits, it'd just be 40 as well. But as long as we have close numbers from the original one, I have 39.997, and they have 39.998. So this is correct. Let's move on now to question 7. I'm glad we're getting all this practice with molar masses. It's always something that you need to use. Oh, this is a very straightforward question, but molar mass is always something that you need, because that's really the only way you can get the grams or get from grams to moles, and a lot of conversion happens surrounding molar mass that it becomes a very crucial part of chemistry. Okay, so now in the question 7, calculate Ka from pKa. Okay, so to do that, actually, there's actually an equation we use. Ka and pKa work the same way as the concentration of H3O and pH. Okay, so if we remember correctly, pH is equal to negative log of H3O plus, okay? So the only way to be able to convert this back is when you have a log without a base, it's just 10. So that's log 10 of H3O, okay? And now, to be able to convert it out, you want to be able to now get the, in a sense, you want to isolate for the H3O part. So the concentration of H3O, actually, what you have to do is you have to do the, to the power of 10, okay? So it would be 10 to the power of pH is equal to 10 to the power of negative log. Let me just make sure I'm doing this right. Negative log, nope, sorry. Almost forgot something before I did that, actually. I want to make sure that you move as many things to the other side first. So it's going to be negative pH is equal to log. There's actually an easy way to do this. Sorry. When you have it written like this, you can do 10. Actually, no, that is the first step. You want to move the negative over. So that's minus pH is equal to log 10 H3O. Okay? And there's going to be 10 to the power of negative pH is equal to concentration of H3O. So that's right here. This is how you go from one equation to the other. But instead of now having the pH and H3O, you want to replace that with pKa and Ka. So actually, if you rewrote it, the actual formula would actually be 10 to the negative Ka. Whoops, sorry, wrong one. pKa is equal to Ka. And yeah, that's all you have to do. Because remember, just think of it as you're solving for a pH, and then you just go back from there. Okay? So exactly, this is correct. And exactly, to understand why we relate pKa to pH is that pKa kind of signifies the, I guess, sort of the acidity of the weak or strong acid. It kind of tells you what pH is probably gonna rest at. That's kind of what pKa implies, and especially becomes very relevant when you're trying to solve for buffer solutions. pKa plays a role there because the pH will be a value that kind of encompasses the pKa. Okay, so now question 8. So, the following is a structural formula for benzene, C6H6. Benzene, okay? Which we studied in chapter 21. And we want 4 parts. You want to first use Vesper, I don't know how to spell right now, VSEPR, predict each HCC bond and CCC bond, okay, in benzene. Okay, B, state hybridization. Okay, C, predict shape, which is kind of already did, and D, draw important resonance structure. Okay, so let's start with the first part. Use the Vesper, predict each HCC and CC bond. So if we actually just wrote this down quickly, well, not quickly, but this is how it looks like, right? If you picked any carbon from there as your center point, okay, you would see that it has at least one double bond to the next carbon and a single bond to the other carbon, and then sticks out a hydrogen. Okay, so this is the what's it called, what it would look like here. And actually the easier thing to be able to do first would actually be B, which would be to state hybridization. Okay, so if you remember, right, hybridization works as in, if you have 4 bonds, like 4 separate bonds, it's a sp3. So 4 single bonds is sp3. Okay, and 3 bonds, so now 1 less, is same thing. It's going to be now sp2. Okay, so this right here, actually the hybridization is sp2, because if you the way it breaks down is that S counts as 1 in a sense, and the P would be the amount of the other left over. So if you had like this, for example, okay, this would just be let me just make sure, it'd be an sp bond if I remember correctly. Well, actually, sorry, yeah, I was missing a part. There we go. If it was bonded like that, it'd be an sp bond because it only has 1, the S, and then that, the P part. So with that being said, this is an sp2 for every hybridization here on the carbons. Okay, and exactly that's what they're asking for. And now that we know it's sp2, in terms of the actual Vesper, if you see it here, we have 3 bonds, right? And 0 lone pairs. Okay, so with that being said, because we have 3 bonds and 0 lone pairs, it's going to be a trigonal planar, if I remember correctly. Okay, that's going to be the shape of it, and because it has that shape, it's going to be, as I said, trigonal planar. Every bond is going to be 120 degrees from each other, because it's kind of like a perfect triangle, if that makes sense. And we do have our Vesper sheet here, exactly 3 bonding groups, 0 lone pairs, trigonal planar. That's what we have here, and exactly that's what it looks like there. So it's flat, and every part is 120 degrees. Okay, so predict each HCC and CC bond angle is going to be 120 degrees for every bond in there, no matter where you go from. If I can draw the whole thing, and you'll notice that still everything is just going to be 120 degrees. You could have another carbon come out here, and then it's going to have the same double bond, and you see here it's still going to be 120 degrees. So with that, we have, now we know that part, and now it says predict shape. So if every bond is 120 degrees, well, we can say that it's going to be trigonal planar, as I said. Okay, but more importantly, right, if you visualize it, the shape is just going to be flat. Like, it's just going to look, if I could explain this with words as much as possible, when you see the benzene ring, it's like there's no, it is a 3D structure, but it'll kind of look like that, okay? Because of the fact that every angle is 120, that's, in terms of its stereochemistry and everything, that's its most stable form. It's going to look extremely flat like that. Not like a bolt or anything like that. No bend, no curvature like that. It's going to be flat, okay? Because exactly, everything is trigonal planar. Okay, so now draw important resonance structure. Okay, now for this I'm actually going to draw the rest of it, so the whole carbon, all right, I mean the whole benzene ring. Okay, and now you know something, right? The order of the double bonds, it goes double, single, double, single, double, single. I could draw this thing the exact same way and just move the double bonds one time over to the right or left. So I can move this one over here, this one over here, and this one over here. Still the same thing. Why? Because exactly, it can be stable both ways. It's important to note this because it's not like we're flipping over the molecule or anything. It's literally saying that the double bond doesn't really care where it is as long as there's always a single bond following it. So when we actually draw the resonance structure, it'll kind of look like this, okay? So exactly what I had drawn was just like the picture, right? But now for the resonance structure, it's fairly similar, but to connote the resonancy, 3, 4, 5, 6, we actually draw something like looks like this, okay? Usually let's make it look a little bit more circular. Oops. So what this is pretty much saying is that the double bonds could be, in a sense, anywhere in the benzene ring, and it keeps switching. Like it's not sticking to one position. The double bonds are kind of always moving in that motion in resonance inside the molecule. Okay, so now as a review, we have done that. We already predicted the shape, we stated hybridization, and we used the Vesper. So let's see now how we did. So exactly, each bond is 120 degrees because of the 3 bonding pairs, and it does say it's sp2 hybridized. And exactly, and they do mention what type of bonds they form. So it's like sigma bonds, like sorry, if I remember correctly, single bonds, and pi bonds like double bonds, or like they connote the double bond part of it. And with that being said, the bond angle of 120 corresponds to trigonal planar, which makes this whole thing flat, hexagon and planar. Okay, so that's what's gonna look like. And then they show the resonance. You see how they flipped over the double bond? That's because exactly that's what it does. So that's what we have here in terms of resonance. It's just going around the benzene ring. You can actually use like in terms of pi bonds to kind of indicate that. But that one I have forgotten how to draw exactly. But so we're not going to do that. But just know that in a sense, the benzene ring would have in total 6 sigma bonds, so 6 single bonds and 6 pi bonds. Or is it 3 pi bonds? It will be 3 pi bonds, and it's shared. Those 3 pi bonds are shared inside the resonance structure. Okay, so yeah, there we go. This is correct. All right, and now let's move on to question 9. How to compute solubility for solubility using, well, solubility KSP using molar solubility. Okay, so molar solubility, okay, let's first find out what that means. Okay, it kind of pretty much means that for every mole, in the sense of that molecule in question, there's a certain amount in terms of moles as well that is made from it. Okay, so let's say if you want to find out the molar solubility of let's use Na3PO4, so sodium phosphate. Okay, if we said the molar solubility was like let's say it was quite soluble, it was 0.02, right? Okay, that means for every Na3PO4, like 1 mole about, this amount comes out and forms exactly the Na3. Whoops, not Na3. The 3Na plus and the PO4 3 minus. Okay. Now this is the part that's important and tricky of it, right? Is that we don't just use this value. We base that value based on the coefficient, okay? Because what we're really saying is that for every Na3PO4, this is the amount here that dissolves like soluble in water. But that means for every of the amount that's dissolved, is going to produce 3 times that amount of Na plus ions, because that's the coefficient here, right? So really we'd have 0.06 here, okay? And the PO4 is going to be coefficient of 1, so it's 0.02 still. Now, to find KSP, right, the formula for it, okay, is just going to be referring to the products, because usually the reactant is just a solid that's dissolving in water, so it is not included in the equation. So we have I guess you can really just say A, B, and now here's the part that's tricky about it. You want to make sure you have the right coefficients of it, okay? That's why I use Na3PO4. I would say we can just say this is X and this is Y, okay? Because if you have more complicated types of like let's say we actually wanted calcium phosphate, that's a good one. Ca3PO4 2, right? That was a really good value, I mean really good number, because the coefficients for each one, you still have 3 calciums, yes, but you would have 2 phosphates, meaning that the Y in that case would be 2. So if you want the KSP, actually, let me use each one. The KSP for Na3PO4, okay, it would be Na, the concentration of Na, which is what we have here, because that's the molar solubility, because they usually just give a value like in molarity, and it'll be to the power of 3. And then PO4, not like how I wrote that, Na plus, there we go, and it'll be to the power of 3, and a concentration of the phosphate ions to no power, because exactly as you see here, it's a 1-to-1 ratio. And if you do the KSP for calcium phosphate, okay, this is where you would have, yep, the calcium still. This is going to be to the power of 3, but the phosphate, because now actually there is a coefficient of 2, it will be PO4 3 minus, okay, to the power of 2. That plugged it in, okay. So exactly, if we did this example for KSP for the Na, it will be 0.06 to the power of 3 times 0.02. So the KSP for this would actually be all the way 1, 2, 3, 4, 5, 6. So it'd be 4. Let me write in a different color. That one with these made up numbers, just to be able to write it down actually next to it, 0.06 cubed and 0.02. It would equal 4.32 times 10 to a negative 1, 2, 3, 4, 5, 6. Okay, that is a KSP value, and KSP kind of works the same way as Ka and Kb, just acid and bases. Pretty much just is saying that when put in water, it's almost like not going to dissolve, or just not that significant. It is considered like a weak dissolving, like you're not really weak acid, weak base, but more so that you always have precipitate, because all that solid is not going to dissolve in the liquid, because it prefers, based on the KSP, to be still in its, solid state. Okay, so now if we do the same thing for KSP for the calcium phosphate, right, you'll actually notice that even though it's going to be the same amount of I guess the 0.2 that may have dissolved from it, okay, is going to be now, this value is going to be 0.06, okay, cubed. But now remember, because of the coefficient, it's going to be double that amount. So it'll be 0.042, okay? And then when you multiply that together, you get 3.46 times 1, 2, 3, 4, 5, 6, 7. 10 to a negative 7. So exactly. That's why it's very important just to do these steps, because at first glance you wouldn't really be able to tell what that KSP value would be. So technically speaking, right, the sodium phosphate is more soluble than the calcium phosphate, which also would make sense as well, considering that like when you think about it, a lot of things that are with sodium are quite soluble. This is just theoretical though. I know there's actual values for it, but theoretically speaking, if the same amount of the solid became like the whole moles per liter, then it's usually the one that has the least constituents in total, because technically 3 plus 1, because that's going to be the coefficients, that'll be 4 versus 5, is the one that's going to be more soluble, because it kind of implies that it's going to be less things multiplied, because you're multiplying tiny numbers, and less things being squared or cubed and such. So that is a summary of how you can find KSP from molar solubility. Let's see how we did. They chose something easier. Silver bromide is just 1-to-1 ratio. So if they said the molar solubility was 5.71 times 10 to the negative 7, you just be multiplied number twice by itself. 5.71 times 10 to the negative 7 times 5.1 times 10 to the negative 7, and that would be the KSP value you get. And they said you don't want to include the AgBr, the silver bromide itself, because it's solid. So exactly, that's what we have here as the formula, KSP AXBY. So this is correct. Okay. And now let's move on to question 10. Okay. And now, with that being said, how many valence electrons does Krypton have if its electron configuration is that? So Krypton, let's look at it real quick. Periodic table. Surprisingly, it actually follows the same rules when you want to actually do it from the previous noble gas. So the question is asking how many valence electrons does Krypton have? Okay, and they're nice to give us an orbital notation, but if we solve this, actually it'd just be started AR, because that's the previous noble gas, and we go through all of them. So we have 4s2, and then remember here when we do the D level, it's 1 minus, so it'll be 3d10 since it's completely filled up, and then we're back to the 4s, 4p6. So if we reorganize this, actually it would be AR, 3d10, 4s2, 4p6. And now it's asking us how many valence electrons does Krypton have. Okay, so actually we use this here to find out. Okay, and there's actually a formula. The formula to find out how many electrons are in that orbital is dependent on the, remember how we had the S, the L, the ML, and MS? Is dependent on the L, because the L tells you, remember, I like to just change this to a different color, bear with me. So remember how if it's an S orbital, oh, I knew it, I know I had it wrong, it's N, not S. N is a number as in the orbital is on, okay? So if we went back over here, just in case there's any confusion. N, I did have N. I don't know why I put S. I always confuse those two letters for some reason. But if we had the S orbital, okay. Alright, remember that L is equal to 0. And then P, L is equal to 1, DL is equal to 2, and FL is equal to 3. So the form of the way it works is that the number of electrons in that subshell, okay, is equal to 2 times 2L plus 1, okay? So you can also just see here how many electrons you may think it has. I feel like this is just a better use, because based on this, from what we know about Krypton, its D, its S, and its p orbital are filled. So we have, let's start with the s orbital, right? L is equal to 0, so we have 2 electrons only, because 2 times 2 is just going to be 0. 2 times 0 is just going to be 0, okay? So it's going to be 0 plus 1, which is still with just 1, and then times 2, that's how you get 2. Now for the p orbital or subshell, we have now 1, so 2 times 1 is going to be 2, plus 1 equals 3, so it's going to be plus 6. And now for the number of electrons for Krypton, okay, it's going to be now same thing. 2 times 2 is 4, plus 1 is equal to 5, times 2 is equal to 10. So the number of electrons, valence electrons in Krypton actually will be 18 valence electrons. Okay, so that is what we have there for the number of valence electrons. Okay, I think they may have mistaken the question, because there are 36 electrons in total for Krypton, but for valence electrons, which is just in the outer shell, ooh, actually even I got it wrong as well. It'll actually just be 8. Why? Because actually this right here, that d orbital, okay, counts in the previous orbital because of the 3. So really there's only this 4s2 4p6. So Krypton on its most outer shell is just the 4s, right? Meaning that we don't even have this plus 10. It'd just be 8 valence electrons. Sorry about that. So just exactly, that's why we actually did the notation here, because it actually shows us that this 3 D10 is from the previous orbital. So with that being said, the valence electron is just going to be 4s2 4p6, which is 8. Okay, we don't use this because the d orbital is in the previous one and there's no f orbital. Okay, let's see what they did. Electron configuration. Since the electron configuration, it is exactly IR. That is exactly what we have. 3d10. We determine the number of electrons in argon, which is 18, added to the number of the electrons in the last few subshells. So I think they missed what the point of the question is incorrect. They only want valence electrons, and that'll be the electrons in the outer shell, which is 8. Remember the whole octet rule and how noble gases prefer to just have 8 electrons. I mean, not noble gases prefer, but they do have 8 electrons in the outer shell, except for helium. It's because of this actually, because you will see that when you get to the p level, the s and the p, you will see that exactly it's usually in the most outer shell. So yeah, that is why it has 8 valence electrons. And yeah, let's move on to the next question. Question 11. So I'm going to take a quick water break here. Okay. What is a molar mass of calcium hydroxide? So good. As a nice little break, more questions about molar mass. So oh, I already gave away the name. Oh, it's already there too. Of calcium hydroxide. So now you remember when we had the sodium hydroxide question, okay? That how it is actually named sodium hydroxide, because it had the sodium as the metal part. This one is now calcium, and the hydroxide is the non-metal part. Okay. And the reason why there's a 2 there is because calcium is usually Ca2 plus based on where it is on the periodic table. And also you can tell by the electron configuration what is in its valence shell. You would actually have, just how we did that last question, calcium would actually be like this, and then 4s2. That would be it. So you can see how it's quite different from Krypton. And exactly, so because it wants to act like a noble gas, it wants to get rid of these two to look most like argon, so that's why you have Ca2 plus. But that's just there from your information. Now they ask for molar mass, so we have 1 calcium plus, now this 2, okay, whoops, this 2 gets applied to both elements in that bracket, so it will be 2 oxygen and 2 hydrogen, okay. So now for calcium it's like 30 something, but I don't want to mess it up, so that, oh, it's 40.08, sorry, oh shoot. But let me actually double check and make sure. Okay, calcium 40.078, so that's the value we're going to use here. Oxygen is 15.999 and hydrogen is 1.008. Okay, so now we have 40.078, and then we have 15, so that's 31.998, and then 2.016. Okay, and then we add it together, 40.078 plus 2.016, 74 point, oops, that's an ugly 4.092 grams per mole is what we have as a molar mass of calcium hydroxide. So definitely a lot heavier than the sodium hydroxide. And yeah, so they had 40.078 and they used 16 and they used 1, hence why their number is slightly different from ours. Okay, and if we wanted to round it based on the lowest significant digits, it would just be 74.09. But yeah, this is correct. And now let's move on to question 12. What would be the formula for diphosphorus pentoxide? I know you can see the answer there, but let me explain why we have that. Diphosphorus pentoxide. So why do we have this formula here, di and pent? Right away, because you have two I guess prefixes, okay, that would actually give you a hint that this is going to be a molecular compound, okay, and not an ionic compound. Or I guess you more likely be call it a covalent, and then you say whether it's polar or non-polar. But yeah, so the reason why is because for ionic compounds, the first part, like the sodium, magnesium and stuff, they never have in fact, both parts actually, the metal and the non-metal, do not have any prefixes with them. So if you see things like even like oxygen disulfate, something like that, just something I made up, that one has or sulfur dioxide, exactly, it's two non-metals because there is a prefix there in the oxide, the di. Now with this, you kind of have to memorize this, right? Because I'm going to list out every up to 5, well actually up to 6, but 1 as a prefix of 1, okay, that'd be mono, okay, and then 2, that's di, 3 is equal to tri, 4 is equal to no, it's not but, okay, that's for when you're naming carbox hydrocarbons. 4 would be tetra, there we go, okay, 5 is equal to penta, and 6 should be hexa, Okay, now using this, right, we just kind of plug it in pretty much. Okay, so we have diphosphorus, right? So that'll be phosphorus 2, and pent, as we said, pent, oxide. So oxide stands for oxygen, so we have O and 5 of them. So the formula for diphosphorus pentoxide is P2O5. Okay, and exactly, they talk about how di means 2, pent means 5. If you want to take a quick picture of this, you definitely can, as I give this a comment saying this is correct. Okay, and we'll move on to question 13. Okay, so sorry about the phone in the background. You can just ignore that for a little bit. Someone will pick it up or just hang up, depending on whether it's a telemarketer. Point being is that for question 13, we want to do several parts of it. They're asking for the molar mass, okay, of butane, which they do give to us, C4H10, which follows the formula of CnH2n plus 2. So that's the A. B, calculate mass of water produced. Oh, my handwriting. Wow. Okay. Produced when 8.80 grams of butane reacts with excess O2, that's oxygen. And C, calculate mass of butane needed to produce 76.2 grams of carbon dioxide. Okay, so with that being said, let's first find out the first act. Yeah, let's do that first, finding the molar mass of butane. Okay, so with that being said, same way, we have 4 carbons, okay, and we have 10 hydrogens. So carbon is 12.011 and hydrogen is 1.008. So we multiply that. 4 times 12.011 is like 48.044, something like that. Okay, that's good. That's what the calculator says. Shoot, I did not mean to do that. Hopefully it takes, okay, good, it's right there still. Whew. So we have carbon 12.011 and the 1.008 times 10, it will be 10.080. Okay, so we have okay, so we have as a total is going to be 58.124 grams per mole. So now we have the first part, the molar mass of butane. So now they're asking us to calculate the mass of water produced when 8.80 grams of butane reacts with excess O2. So with that being said, this is a combustion equation. So they kind of imply they need to know what a combustion equation does. So we know that, well, not we know. What we do know is that C4H10, okay? Combustion is just when it reacts with oxygen, hence why they mentioned excess O2 plus energy, okay? Is going to be now CO2 plus H2O, okay, in gas form. Now, with that being said, it could be liquid or gas from what they start with, but the point being is that we need to now figure out how much CO2 and H2O is produced. Okay, so to know that, we have to balance our equation. Okay, so we have 4 carbons here, meaning that we need 4 CO2 and we have 10 hydrogens here, meaning that we need 5 H2O. Okay, that will be how you balance that. But we're not done yet, because now we know how many oxygens we have in total. It will be 4 times 2, that's 8 oxygens, plus 5, we need 13 oxygens. But we have O2 here. I mean, the only way to actually make this fit is by doubling everything to now we have 26 oxygens, because that would make this 2, that would make this 8, and this 10. So it'd be 2, 13, 8, and 10. Let's see if we got that right. We balanced it out. Well, they left it in halves, but yeah, 1, 13 over 2, 4, and 5. Exactly. I just like to keep everything in whole numbers, because that is the, I guess, the moles you'll see in nature. You won't really see half a mole of O2. You wouldn't see oxygen by itself. It'll always be O2. So now that we have the formula, that's why I only scroll down to that far to give you a little hint. To find out how much when 8.80 grams of butane reacts with excess O2, we need to convert that grams into moles using our molar mass. So we have 8.80, okay, grams times 1 mole, because we have to make sure we put in the numerator what we want and what we had to cancel out. 58.124 grams. These two cancel out. So how much moles do we have? 8.8 divided that 58.124. We have 0.151 moles of C4H10. Okay. So now that we have that, actually, what we want to do, they're asking the mass of water. Okay, so not only do they want H2O, they want the mass of it. So we convert again. So 0.151 moles of C4H10. And you're probably wondering what we convert it with. Well, we know what we have, which is a C4H10. So to cancel that, we need it in the denominator. So for every 2, based on our filled equation of 2 moles of C4H10, we have 10 moles of H2O. So in total, you're really just multiplying by 5, and that gives you your moles. So we have 0.757 mole of H2O, but they're not asking for the moles, they're asking for the grams, which is why we need, again, the molar mass of water. So same way, but I'm going to do it a little bit tinier. H2O is 2H10, so that's 2.016 plus 15.999 together. Okay, 18.015 grams per mole. We throw that into the equation, 757 moles of H2O, and we don't want moles anymore, and 18.015 grams. So this times that 7.757, we have in total 13 point, let's see if we need to round, because they have only 3 significant digits in the 8.80. So 13.6, we want 3 significant digits. Okay, grams of H2O. That is our answer when excess oxygen, aka it's not a limiting reagent, the limiting is the butane, reacts with the limited amount of 8.80 grams of butane. So that's what happens there. Now they're asking, calculate the mass of butane needed to produce 76.2 grams of carbon dioxide. So this one we kind of have to now work backwards, okay? So we know 76.2, right? And if we did the same thing here, carbon dioxide, 1 carbon, 2 oxygen, that is equal to 12.011, 31.998, add together. Okay, that's 44.009 for CO2. Okay, that's carbon dioxide. So 76.2 grams. Okay, and now we know how much grams per mole. 1 mole of CO2. These two cancel out. So now we have 76.2 divided by that. That's a whole 1.73 moles, okay, of CO2. And then based on the conversion factor here, there is 2 butanes produced for every, 8 CO2 produced for every 2 butane. So if we put that in the equation here, we have the, CO2 we needed, and then we want to go to butane. So that'll be 2 C4H10, so that's 2 moles, sorry, and 8 moles of CO2. So really all you're doing is just dividing by 4. Divided by 4, so you have 0.433 moles of C4H10. Okay, and now the last part is we refer back to our molar mass up here. So to get from moles to grams, it'll be 0.433 moles times 1 mole of the C4H10 is equal to 58.124 grams of C4H10. Okay, and now what do we get? 58.124 times that value, 25.1. Well, if you round it properly, 25.2. Okay, so there's 25.2 grams of C4H. So I can write that better. C4H10 needed to produce 76.2 grams of carbon dioxide. Okay, so let's see how we did. So exactly, we definitely got that molar mass part correct. 58.12, slightly different because they have different values for their oxygen and carbon. So now with that being said, as we do our work, yep, they got 13.6 grams of water, which is good. And for their carbons, as they're breaking it down, they also got 25.2. Perfect. So with that all being said, this is correct. Okay, and that is for question 13. So now we're officially moving to question 14. So it's asking us to label each of the following compound of the label each of the following as atomic element, molecular element, or compound. So for this question, it may seem relatively simple, but we first need to really understand what it means for each one. So an atomic element, okay, based on at least this question, is something that's by itself. Okay, no other parts, one, I guess, sphere. That is an atomic element. A molecular element, so it still has that element in its name, is two of the same sphere. Okay, so same color, same element. An example of that would be like O2 as a per example of a molecular element. An example of atomic element is like sodium and A. Okay, that's an example of atomic element. This is an example of a molecular element. Okay, Now for the last one, a compound is two or more of different things. Okay. An example of this would be like NO2. Okay. So different spheres, different colors, and everything like that. Okay. So now let's go back to this question. Okay. For A, we have right away a red, black, red. Okay. So it doesn't really matter what it is, but we know that that means it's made up of two or more different things. Okay, because you have a red and a black. Okay. That will make A a compound. Okay. Gosh, oof, can't even write compound down. And now B, same process. We have two little, it seems like light blue or white, and one red. So different things again. This will also be a compound. Okay. C. Now we have two of the same color. So this is actually a molecular element because we have two blues, two of the same spheres. D, as you probably guessed, just one sphere by itself is going to be an atomic element. Sorry. Okay. E, I'm just going to write down these as well. But E, exactly. Two of the same looking things. So again, it's a molecular element. Okay. F has two different colors. So two light blue spheres, two red spheres. So that would actually be a compound. And G, the last one, as you probably tell, looks kind of like D over there, or just one thing. That is an atomic element. Okay, and that's really how you break this down in terms of what these names mean. So let's see how we did. Based on this, compound, compound, molecular element, atomic element, molecular element, compound, atomic element. Perfect. This is correct. Now let's move on to question 14, or is it 15 now? 15 now, it seems. What is the electron geometry and molecular geometry for BeCl2? So the first thing we want to do is write down the question is the electron geometry and molecular geometry of BeCl2. Okay, so as they said there, actually the first step after I write the question down is to draw this Lewis dot diagram and refer this to our periodic table. Okay, so beryllium, okay, if you see here, it's going to be on the second column, meaning that it's going to have two electrons. That's what it can contribute, because that'll be its most outer shell, its valence shell. If you wrote it out, you'd be able to see when you write the electron configuration, it would be helium 2s2. Okay, that would be beryllium. Chlorine has a hole, as we see here, all the way down here, okay, can provide 7 electrons. And you can tell if you write it in its electron configuration, it would be neon, okay, and it'd be 3s2, 3p5, okay. That would be chlorine right there. So now we know that beryllium gives 2, chlorine gives 7, but there's 2 of them, so it will be 7 times 2. In total, you need 14 plus 2, 16 electrons in your Lewis dot diagram. So let's draw it out. So beryllium only really has room for for a single bond on each side, because that's how it started. Like, it only had 2. It wouldn't really aim for that octet rule, which is convenient because chlorine is going to be on each side of it. Okay, and then we kind of fill out the shells of chlorine. Okay, and once you do that, you actually see and realize here that chlorine is now has 8 on each one, and really, there we go. This right here will be beryllium chloride. So with that being said, now that we have the Lewis dot diagram, we can convert this into what it would look like as a molecule by just turning these into bonds. Okay, and it can actually count exactly. We have 16, which fulfills the criteria. And if we want the oxidation number for each one, beryllium, as we said, 2 valence electrons, and it's going to be, it's not plus, minus how many lone pairs it has, which is 0, minus the electrons and bonds divided by 2, which is actually 0 still, because 2 minus 2, that's perfect. And each chlorine, 7 minus, we have now 6 on the valence electrons and 2 over 2, which is 0 as well. So this is perfect for beryllium chloride. So now geometry, this right here, beryllium, because it only has 2, okay, it'll be an sp hybridization, okay. And now going beyond that, to figure out what shape is going to be, as you can tell, it's going to be relatively linear, but more importantly, you see that you have 2 bonds, okay, and 0 lone pairs. Okay. Okay. So because of that, actually, its electron geometry and molecular geometry are just going to both be linear. Okay. And we can actually check the Vesper theory here on the sheet. 2 electron groups. Exactly. Electron geometry linear, molecular geometry linear. So that's the answer here for question 15. It's just going to be linear. And now let's move on to question 16. Well, first let's see how we did. Kind of assume we're right, but exactly, linear, perfect. That's exactly what we want. This is correct. Now let's see what we have for question 16. What is a molar mass? Ooh. Mass of benzene. So remember that question we had earlier of the whole benzene and the ring and its resonance? Remember how it was C, 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 C. This is something you have to memorize, but I'm actually just drawing this out just so that you can remember from that question. Okay. So when I draw it out like that, right, it makes it actually a lot easier for you to, you know, go ahead and count it. So with that being said, the formula for benzene is C6, which is something you have to memorize. If it's easier for you to memorize a picture, I will start there and then count it out. But yeah, let me just draw that resonance. C6H6 is your formula for benzene. So now that we know that, we follow the same rules, okay? 6 carbons, 6 hydrogens, okay? And we have 12.011, 1.008. And so that would equal 12 times 6. That would be 72.066, and then 6.048. Okay? And we add that together. 6.048. And I'm just using the numbers provided from the periodic table. Okay? And we get 78.114. So the molar mass of benzene, okay, is 78.114 grams per mole. Okay? And theirs is slightly different just because they had different values for carbon and hydrogen. But yeah, other than that, that is how you solve this question. Okay? And now, question 17. Molar mass of sodium carbonate. So you know you can see the question, the answer there of what sodium carbonate is. But these are the things you have to memorize as well. A lot of memorization when it comes to especially this part, what that means. Because we know that sodium is just going to be Na, okay? And we know it's a plus because the whole electron configuration and its row on its periodic table is just going to be neon 3s1, okay? So you see the 1 there, and it likes to give out 1 electron to kind of be like a noble gas. Carbonate, okay, we have the clue there. Based on the other questions we solved, where remember how the 8 means a certain amount of oxygens, okay? And carbon, that just means carbon. So we have CO something. So carbonate in its most, stable form, the 8 would actually mean 3, okay? CO3, that's carbonate, okay? That's a carbonate ion. And it'd actually be 2 minus. And to check that out, remember that carbon will be that +4, oxygen is -2. Okay, and there's 3 of them, so that's -6. Yep, math checks out. Because in total we have -2, well, -2. And so, with that being said, let's see here in terms of what we can do. Exactly, so now we have 2 minus for the charge and +1 for this charge. So we need to balance this out. So we need to multiply this times 2 to make sure we have a net charge of 0, which makes it no charge. So that'd be Na2CO3, and this right here is a formula for sodium carbonate. But we're not done. It's asking for the mass of it. So same way, 2Na 1C3O, that'd be 22.990. Carbon is 12.011, and oxygen is 15.999. Okay, that'd be 45 point, I need a calculator, times 2, 45.980, 12.011 still, and then 47.994. Okay, and then we add them all together. Oops, I think I got that wrong. It'd be 47.997. I'm glad I double checked. So with that being said, plus 12.011 plus 45.980, okay, we have 105.988 grams per mole. This is our molar mass of sodium carbonate. Okay, now let's see how we did. Yep, it's around the same. 105.99, just because of their values they use in their periodic table. But other than that, this is correct. So we've gotten quite familiar through this session with how to find molar mass. Hopefully, as we do these questions, it becomes more and more, it becomes easier for you to just refer to the periodic table, So now this question is asking for the electron configuration for a phosphide ion. Okay, so now to answer this question, first I have to answer the question of what is a phosphide ion. So let's actually use other elements to be able to figure that out. We have NaCl. The name of that is sodium chloride, ending with IDE. Okay, so when things end with the IDE, okay, it means that it's just going to be the element of that element they're referring to, in this case being phosphorus. So phosphide ion would mean that, well, let's just start with what phosphorus is. So we know that now it's a phosphorus. Okay, so before we jump to solving for the ion, we first need to solve the electron configuration for phosphorus by itself. Okay, So that would actually be, okay, if we start it from the neon, oops, I don't like this color, neon, because I want to differentiate from the question itself, is going to be 3s2 3p3, okay? Now that means it's 3 away from becoming a noble gas. It could either lose 5 whole electrons or add those 3, which is where the ion comes into the play, okay? Because now to get to that noble gas setup, you really just want to throw in 3 more electrons. So it will be 3 more electrons added to that p shell, since the s shell is full. So for the phosphide ion, the electron configuration will be 3s2 3p6. That because it's 3 minus there, because when you add electrons, you actually it's a negative sign because electrons are negative. So this right here actually should denote the electron configuration for a phosphide ion. Okay, yep, 3s2 3p6. There we go. So it's a lot easier to gain those 3 than to lose a whole 5, hence why we jump up like that. This is correct. And now let's move on to question 19 for today. How do you calculate the pH of HCl? I am so glad they had this. But let me just write the question down. To calculate pH of HCl. So I wish I could just copy and paste what I said earlier about the whole acetic acid, but the first thing exactly want to do is find Ka to know if it's strong or weak acid, okay? So when we refer back to this table, hydrochloric acid HCl is all the way up here, and it actually gives an answer right there. Strong acids, Ka greater than 1, which is actually what all these are. These are the strong acids that we know of, hence why they're up there. So hydrochloric acid is a strong acid. In fact, I'd actually memorize that because hydrochloric acid is quite reoccurring in chemistry, and you just have to know it's a strong acid. So it is indeed a strong acid because the Ka is greater than 1. Okay? Now, with that being said, the formula now for dissociation would actually be HCl with not much need of water, but you can still add that there too if you want, but it just go like that. H plus Cl minus. You could also write this when it's actually reacting with the water, whichever one helps you see the dissociation easier, but it will be Cl minus plus H3O. Okay, and the reason why the arrows are like that, because it's a complete dissociation. Okay, and either word will say the same thing. Okay, the point being is that to calculate the pH of HCl, because it's a strong acid, it's a 1-to-1 ratio. You don't even need that whole Ka formula. Whatever concentration, so molarity, whatever molarity you have of HCl, you will have the same molarity of the Cl minus. If you start out with 0.5, and the H plus, sorry. If you start with the 0.5 moles per liter of HCl, you'd have 0.5 moles per liter of that H3O hydronium ions, or just like that, quote unquote, the acid component. And then you just throw in your formula, negative log H3O, right? And you just factor in whatever value really you have. So if they give you like the grams of HCl in a certain amount of solution, as long as you can find the molarity of HCl in that solution, you have found your molarity of acid. So together with those two things, just throw that into this formula. And in this example, for example, the pH of that HCl, negative log of 0.5, the pH would all be all the way down at 0.30, which makes sense because hydrochloric acid is a strong acid, so it's really close to like 0. And exactly in this case they used 0.2, and when you do the same thing, negative log of 0.2, we have it rounds up to 0.7. So exactly, strong acids, it's just a 1-to-1 conversion as they showed here. Okay, every 1 mole of HCl, there's 1 mole of H3O formed. And they actually did use this formula as well of the second one. Either one works, like this one and this one, as long as you know that the H plus is the same thing as the H3O plus. Okay, but in terms of technicality, it is H3O plus. They're hydronium ions. It's hard to see like just I guess proton just floating in the water. It's usually the protons being grabbed by other molecules to form things. Okay, and now for question 20. Final question for today. What is the structure of C6H12? Unfortunately, you see the answer right there. So I do have another question for this, which is going to be what type of molecule is this? Yes. Okay. And name. Although they give the name as well from the answer. But the way you want to draw this out, right? You want to start with your carbons and hydrogens, okay? So C6, I just like drawing like that. Sorry, I like this better. Don't know how I can't draw these things. Okay, so that's C6 right there. And the way it works is that you want to make sure that the oxygen really could go anywhere, really, because as soon as you put oxygen anywhere, every other part will have to be a hydrogen of what it can fit. So you can see here, it's going to be like that, and then this is already taken. Okay, and you count, all the greens are hydrogens, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this also is C6H12O, okay? And this is an example of, I guess, when you have, what are they called? Structural isomers? Yeah, structural isomers, because we can either get ketones or aldehydes. Okay, and the one they have here, where they have it drawn like this, okay, and they have the oxygen at the end, all right, and then they have the hydrogens bonded like that. Okay, still have 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This right here is the aldehyde, okay, because, and it's like that's the type of molecule because the oxygen bond is at the end. Ketones, the oxygen bond is inside the actual structure. So in terms of the name, actually, actually I'll leave like that. Actually, in terms of naming, right, they have the name of the aldehyde, which is gonna be like, typically you see 6 carbons, so that'll be hexane. Okay, but instead of the ane, you drop the E and add an Al there. Okay, so you have hexanol. All right, so that will be the aldehyde name for that. Now for ketones, okay, honestly I do not remember how to name them, so I will actually have to ketone naming. So I do believe there's a specific way of doing it. Let's see. There we go. We can use a textbook. Always refer back to the textbooks if you're ever unsure. So ketones like that, they have the Al for aldehydes. Now for ketones, we have, there we go, ketones is going to end with O-N-E. So we see it's just O-N-E at the end, and you put it where the oxygen shows up, and you try to get it as close to the, I guess, carbon, like where the number will be less. So here we have 1, 2, 3, 4, 5, 6. If you went the other way, it'd be on the fourth one. So this the name for this would be 3. Still the same hexane part, okay, but instead of it being hexane, it will be replace the E with a O-N-E, so 3-hexanone. So hopefully if I type that in, 3-hexanone, we would get, yep, C6H12O. Now with this, yep, that is exactly what we've drawn here. The thing is, though, is that this question, I would say that this technically is correct, because I do mention, however, other structures are possible. But the thing you have to remember is that this is just one example of a ketone that you can form from that structure. You can have the oxygen show up here, here, and here. So there's 4 more spots for the ketone, and it'll have each a different name. Whether it's 2, technically you would either have 2-hexanone or 3-hexanone. Because once you get to these parts, like the 5 and the 4, it will now be this as your new 1 at this end right here. Okay, so probably these are really the only ones you can really get. But for hexanol, because the O is always going to be at the ends, you really just have hexanol, whether it's on one end or the other. So these are really like most of the possible structures for this. There's probably other structures out there, which is why they're called structural isomers, and these are just examples of structural isomers for C6H12O. So it depends, honestly, the answer depends on what your professor is asking for. So I just watch out for that when you're given just the elements, like not the actual name for it. It leaves a lot of possibilities to what it could actually be when you're just given the molecular structure. I mean, well, the molecular name, C6H12. All right. So with that being said, that is it for today. I just want to thank you again for joining us in this stream. I hope you have a lovely rest of the day. And yeah, if you have any further questions, definitely check in the links in the description below. We're always here to help. And yeah, if you like the content, keep checking it out. We'll just keep answering some more questions, and hopefully we'll touch on the question that's been on your mind. All right. Have a great rest of your day.